We're going to start with a puzzle. So you all know quantum mechanics now? So if I have an atom and it has some energy levels, so this might be the ground state, first excited state, and so on. If I start out in an eigenstate, or if I start out in some coherent superposition of two eigenstates, what do we know is going to happen physically? I have an atom, it's in an excited state. What happens to atoms in excited states? How many of you think you know the answer, but are too shy to say? Wow. Come on. What's going to happen after a sufficiently long time? Yeah, it'll decay to the ground state, right? Things decay, unfortunately. You'll have a atomic decay process, and photon will be emitted. The atom goes to its ground state, and it's happy. Does that make sense? For how many of you do you feel like you should have known that answer? One? Only one of you thinks you should have known the answer to that? My goodness, don't you all have undergrad degrees in physics? Wow. Okay, so then this is going to be a tougher puzzle than I thought. Now, next the question is, accept that this is true, that this is what happens to atoms. States typically have some lifetime, and after a time scale that's a few multiples of that lifetime, with very high likelihood, you will find it in a ground state. Now, the next question is, how do we show this using quantum mechanics? So let's do this in a few pieces. So what happens? How do I model? What's the simplest model for the time evolution of this atom? Sorry? Right. So we can imagine the atom. So we say the atom at t equals 0 is in some state, psi of t equals 0. We assume it's an excited state. So psi at t equals 0 is going to be some superposition alpha 1 E1 plus alpha 2 E2 plus 0 E0. So here I'm imagining that it's a coherent superposition. I don't know what that symbol means, but the point is these two energy levels are populated. The probability of finding it in state E1 is alpha 1 squared is the probability of finding it in eigenstate E1. The probability of finding it in eigenstate E2 is alpha 2 squared. And the probability of finding it in eigenstate E0 is 0. So it's in some excited state. We can equally well just, for simplicity now, let's just remove this guy and let alpha squared equal 1 for simplicity. So we're in the first excited state. The higher energy levels are negligible. There's no physical reason to expect those to become populated. However, we do have a physical reason to expect the eigenstate E0 to become populated. So we write down the Hamiltonian for the atom. And it's going to be some energy levels. So it's going to be some structure where EL hat is a projector onto EL. So it has some energy level structure. This is going to induce a time evolution. If we start out in the eigenstate E1, what's going to happen under this time evolution? I heard a whisper of the solution over here. It stays there, right. So E1 isn't energy eigenstate. What that means is that it's stationary under the evolution of the Hamiltonian. So how do we get an atomic decay? Perturbation theory, that's part of the answer. Spontaneous emission is the answer, but how do we get it? Very good. So in order to understand why atoms decay, we have to remember that the Hamiltonian is equal to the Hamiltonian of the atom tensored with identity plus the Hamiltonian of the vacuum and that the initial state is actually not just the eigenstate of the atom, but the initial state is a composite vector, which is equal to alpha 1, E1 tensor the zero state in the vacuum. And then what's going to happen oh, and plus I'm missing something here. I'm missing the interaction Hamiltonian, which is the coupling between the atom and the vacuum. And now, I mean, this is the key piece. When you take into account this interaction term, then this state is no longer an eigenstate of the full Hamiltonian. It's an eigenstate of the atom plus the vacuum. But this is no longer an eigenstate of the Hamiltonian, which includes the physical coupling between the vacuum and the atom. Yes?
So in chronometry, we are told that the vacuum is fluctuating state. But in quantum mechanics, how do we know this? What is H vacuum in quantum mechanics?
I think H vacuum, okay, so I think that H vacuum is just the harmonic oscillator for each mode of the, so you have a continuum of modes in the vacuum, which all are unpopulated, so they're all in their ground state. And then when a photon is created by some process, then that's an excitation in one of the modes. It's the mode associated with a particular frequency and a particular direction of propagation of the photon. So I think the vacuum is just that, where these are the raising and lowering operators, and I may have the order of the daggers reversed here. And there may be constants here that I'm forgetting about. So let me just throw some scalar in here. Let me call it alpha n. And, you know, people say the fluctuating vacuum. And one thing I've never sorted out, and I would like to know, is how to understand that kind of from an epistemic point of view. I bet Rob Speckens probably knows how to do that. But so, yeah. Okay, so this is just a little story that shows you that the things we're about to look at in the lecture for open quantum systems, while it's definitely highly motivated by the context of the current technological paradigm, which is that we're trying to learn how to control and manipulate individual systems, and taking into account the open system nature, which is more or less inevitable, is crucial for being able to achieve that goal. And so while it's very relevant to the forefront of physics, the forefront of experimental physics, it's also relevant just in a very kind of fundamental way of understanding basic ideas of how systems behave when they're coupled to other degrees of freedom that you're not taking into account. And so this is kind of a nice little story motivating this open system picture. So what I'd like to do now is give you a description of this. So first I'll just describe the kind of the simplest level description of an atom-photon coupling, atom-vacuum coupling. Calling it the vacuum is really the wrong thing. Really, it's the Hamiltonian for the electromagnetic field. And the electromagnetic field, even though it might be unoccupied by any photons, is still a system with the Hamiltonian. So just like when atoms are in their ground state, we can still write down their Hamiltonian. Similarly, when an electromagnetic field is in its ground state, which is the vacuum, we can still write down the Hamiltonian. So I shouldn't call this the vacuum. This is bad notation. So let me undo that. And the point is that this state then is the vacuum state. And this 0 here is compact notation for 0 tensor 0 tensor 0 tensor 0, where you put 1 0 for every continuum of different possible frequency and direction the photon can take. So all these different modes. Now, when you create a system that's somehow bound, so if you have a cavity, for example, as opposed to the infinity of space, then that cuts down on the allowed modes of the electromagnetic field. And so just bear that in mind, that difference is relevant when you come across those situations. But here we're just imagining an atom not in a cavity, but just out in space. We want to understand what its dynamics will be. And so you can use something called the Jaynes-Cummings model to describe this interaction in detail. What I'm going to give you is what was historically done first, probably, which is just the phenomenological description of the atom system alone, where we add a phenomenological noise term that takes into account what you can get through an exact treatment of this Hamiltonian in, say, the Jaynes-Cummings model or something like that. So we're going to look at a phenomenological And then once I give you this simple phenomenological model, then I'll give you some broader theoretical framework in which this phenomenological model emerges as a special case. So that's where we're going after this example. Okay, so I hope that I don't run into trouble because I'm giving this lecture now backwards because I decided this was a nicer story earlier this morning. So this is backwards from the way it's presented in my Open Quantum Systems course notes, which is available to all of you. So we're going to consider a driven two-level atom and what are called the optical block equations. So what that means is that the transition between our two energy states of our atom, which is here, so we're going to consider these two, the first excited state and the ground state, and then we're going to imagine that we actually are applying a laser whose frequency is close to the energy difference between the two levels. So when we say it's driven, what that means is that the driving is provided by a single E&M mode and then we have E1 minus E2 will be, for notational reasons that I don't recall, is going to be written this way. So So even though E1 is greater than E0, we're putting a minus sign here, which means we're making the frequency negative. So if that bothers you, you can undo this. For some reason, I did it this way, and I don't remember why. It's just a minus sign, so we don't need to stress about it too much. But then we can write down the Hamiltonian H naught is equal to H bar omega naught sigma z over 2. So here, you kind of get a first window into what we do in quantum information, which is we're interested usually in two-level systems. So it doesn't matter where those two levels come from. Here we're just saying, well, let's just interpret the first two levels of the atom as the up and down eigenstates of some operator sigma z. Okay, so the mathematics is equivalent. So we're not talking about the spin degree of freedom here. We're just using this abstract mathematical operator, sigma z, as an operator which corresponds, I mean, basically all we're really saying here is that sigma z, which is equal to 0, 0, minus 1, 1, mathematically, we can think of as E0, E0, minus E1, E1. Or I hope I got the order right there. Yeah, I did. Good. Okay. So now the electromagnetic mode has frequency omega. And in general, omega is going to be approximately equal to omega naught. And in fact, we're going to define a quantity delta, which is equal to omega minus omega naught. And this is called the detuning. It's also if delta is non-zero, then we say you're off resonance. So the further off resonance you are, the less well you couple to those two levels. And eventually, if delta is big enough, then you have essentially a negligible interaction. So another way to think about what we're doing in this phenomenological model is that instead of treating the electromagnetic field and the vacuum and the electromagnetic state quantum mechanically, we're going to treat the electromagnetic field classically, and that'll force us to have a phenomenological model for the decay process. So we imagine a classical EM wave which is just E equal to some polarization vector ES, a magnitude, and an oscillation. Where here omega is the frequency of the mode, and ES is the polarization vector, I think. Yeah. Good. And so then we can model the interaction Hamiltonian in the dipole approximation. So the coupling between the actual electromagnetic field and the atom is a little bit more complicated than the form we're going to use. The form we're going to use is an approximate form, which is sufficient for our purposes. Which is, oh, you guys can't see this here, so I'll go over here. So our interaction Hamiltonian is equal to H bar omega 1 cosine omega t sigma x. Now this is an interaction Hamiltonian, but the only operator in this expression is the system operator, exactly because we're treating the electromagnetic field classically in this model. And sigma x is an operator that can induce transitions between the two atomic eigenstates. I should write E0, E1 plus E1, E0 here. Or you can just leave that notation if you're comfortable with it. And omega 1 is, and this is where the dipole approximation comes into play, is given by the magnitude of the electromagnetic field E0 d dot E E1. And I think that there's a typo in my notes because this shouldn't be E. This should be ES. So basically, the dipole operator is given by the charge of the electron. So remember, an atom, this is actually essentially, it's loosely speaking, it's the position of the electron is what's giving us these different possible levels of the atom. And so we're concerned with the charge of the electron as well as the position of the electron relative to the nucleus. So here we're working in a reference frame. R is the vector between the nucleus and the electron. So you can see how all the relevant physics is here. Basically, the strength of the electromagnetic field so notice the frequency of the field shows up here, the strength of the field here, the polarization of the polarization vector couples to the dipole moment of the electron nuclear system. And this gives us a transition amplitude. Am I using E0 for two different things? Oh, I am. Yes. Yes, thank you. That is unfortunate. Yeah, so in my notes I call it EG. And sadly I set this up as, you're right. So let's call this, EF for E field. So let me try and retroactively fix this. So this would be an EF here. Thanks for catching that, Tibra. So this is the so-called dipole approximation, which models the classical field coupling to the atom. Now the state is given by some vector rho, and this is the state of the two-level system. And we can write this as rho 0, 0 of t, rho 0, 1 of t, rho 1, 0 of t, rho 1, 1 of t. Where these are obviously the scalar complex numbers, which are the matrix elements. And we know that rho 0, 0 and rho 1, 1 are not complex, but non-negative. They're the populations, so they're probabilities. The diagonal is always probabilities. And then the off-diagonal terms can be complex, and they correspond to the coherence between these two levels. And then for ease of notation, what we do is we just define a quantity delta, which is equal to rho 1, 1 of t minus rho 0, 0 of t. And that's obviously real. And we define a quantity r, which is equal to rho 0, 1. And and that's sufficient. So why are these two parameters sufficient? I mean, we have 4 complex numbers. We've decided these two are real, or in fact non-negative. So why do we only need 2 real parameters to characterize what's happening here? Actually, R probably isn't real. I think R is not real, actually. So we have 3 parameters. Why is that? I'm sorry? Right. So rho 1, 0 is rho 0, 1 conjugate because the density operator is Hermitian. And the trace is 1 because the populations add to 1. So this reduces the number of parameters. And so presumably this is complex. Okay, it's a quick question. So if I have a D, for a D-dimensional state operator, can you calculate how many independent parameters are needed to specify the state for a D-level system? It's a counting argument. So I'll just mention this as an aside. For a D-level quantum system, a preparation of that system is specified by D minus 1 diagonal terms, where the minus 1 is due to the normalization. Probabilities add to 1. And then we have off-diagonal terms. In general, for a D by D matrix, the number of off-diagonal terms is, what is it? Is it like D times D minus 1 over 2? But they're complex, so we multiply by 2. So what do we have? We have D plus 1 times D minus 1, I hope. D squared plus D minus D minus 1. So you need D squared minus 1 real parameters. It's a useful thing to know. Okay. So now our Hamiltonian is equal to H naught plus h int. And the dynamics are given by the von Neumann equation. IH bar d rho by dt is equal to the commutator of h with rho. And then using I'll state without deriving the result in terms of these parameters. It is easy to show that the dynamics we get are the following. And so this is a model of atomic levels driven by incident electromagnetic wave in the dipole approximation. Now, because our classical electromagnetic wave, because our electromagnetic wave is classical, and because we're treating the whole electromagnetic field as classical, there's no decay in this. Basically, what's happening is that the laser is driving the atom state between E1 and E0 in a coherent oscillatory fashion. So we have this gives coherent oscillations. So then we're going to put in the atomic decay process in phenomenologically. But before we do that, I want to go to the rotating frame. Oh, I shouldn't have done this. All right, I'm not going to go to the rotating frame. So I won't go to the rotating frame. So in order to model atomic decay, we insert new terms. So by the way, these are called we'll get it in a minute. So how do we do this? So first we want to define a notion of an equilibrium. So we can say that let delta equilibrium be the kind of, so we're doing this by hand. This is phenomenological. Be the kind of equilibrium populations we want to model. Typically, one might do this taking into account the Boltzmann factor for the probability of a different level. So if this atom is in some heat bath, there's a slightly higher probability of it being in the ground state than in the excited state, but there's a non-zero probability of it being in the excited state because of the heat bath it's in. So for example, one might have rho 1, 1 in equilibrium divided by rho 0, 0 in equilibrium is equal to e to the minus delta E over kBT. This is the familiar Boltzmann factor. So for spontaneous emission, we take into account that the for spontaneous emission, we say that the energy level E1 has a lifetime gamma 1 which is equal to 1 over T1. I got this wrong. The lifetime is T1 and gamma 1 is the decay rate, which is the inverse of the lifetime. I think I'm not forgetting factors of 2 pi here. Let me just quickly scan my notes and see if I... Yeah, no, that's right. So in practice, one can actually calculate this lifetime from first principles by quantizing the electromagnetic field and carrying out a detailed calculation. Here we're doing an easier phenomenological model, as I've mentioned several times. And then one models the decay, one models exponential decay. With lifetime T1 by adding the following terms to our differential equation. Minus gamma 1 times the factor delta minus delta equilibrium. So when delta reaches the equilibrium factor, when delta equals the equilibrium delta, which we put in by hand as being the equilibrium we expect to reach, then you can see that this term contributes 0. So there's no longer any transitions between the energy levels. Yeah?
I'm not sure what you mean by delta.
Well, delta was defined as the difference between the populations. And so the point is that we have to decide, if we're doing a phenomenological model, we have to decide, well, once the atoms reach a certain rate difference between the two populations, when is it happy? When is it no longer going to? Basically, what's going on here is there's two competing mechanisms. One is that the thermal bath is exciting the atom occasionally. And the other mechanism is that the coupling to the electromagnetic field is leading to spontaneous decay of the excited state. So those two competing processes will lead, when treated exactly, will give you some equilibrium populations. And so if you start out of equilibrium, then the system will be driven to the equilibrium value. Whether that means that the population of the ground state will increase or decrease depends on how you start out. So it turns out, and this is a property of quantum mechanics, it's impossible to have a process which changes the populations without also dephasing the coherence between those two levels. When I say impossible, I mean it violates the complete positivity of the map. This was proven by Proguvecki some 30, 40 years ago, and it's also, the details of that are in my course notes if you're interested in the Open Quantum System course notes. And so basically, so these terms then, these terms give us the, I mean, that's a bad way to designate these terms. So these terms correspond to, so this is the, this term is the non-unitary decay, and this term is the inevitable dephasing associated with, and dephasing means attenuation of coherence. So attenuation of the off-diagonal term. So you see here that R, remember R is the off-diagonal term, and if you all remember your differential equations, if you ignore the coherent dynamics, then dr by dt is equal to minus gamma 1 R is an exponential attenuation of the coherence. And in general, you can have a factor here which is larger than gamma 1 over 2 if you have additional mechanisms leading to dephasing. And when we discuss the NMR example, we'll see that. But if the only thing you're putting in is this decay due to spontaneous emission, then this is the minimum amount of dephasing you can have. So this set of equations are very famous, and they're called the optical block equations. Okay, are there any questions about this model? Because what I'm going to do next is talk about the situation of nuclear magnetic resonance, where you have a nuclear dipole which has a spin associated with it, a nucleus which has a spin associated with it, and the spin can be up or down relative to some external magnetic field. And then one can drive those two levels. Instead of using light, typically one uses radio frequency electromagnetic modes to couple to that energy gap, because it's a much smaller energy gap. And so I can go on and do that. Yes? What I mean is that you can't model this with a unitary acting on the system alone. So remember, in the last couple of lectures, we looked at what happened when you have a unitary on a system and an environment. So we treat the environment quantum mechanically. And then we derived that the effective dynamics on the system is modeled by Krauss operators. And I've mentioned how those Krauss operators correspond to a discrete time process of the system, which is not describable by a unitary on the system. We need a more general mathematical framework to account for what's being neglected when we ignore the other system, which is part of that unitary transformation. So you can think of Krauss operators as being a model of a non-unitary process. I mean, it is unitary in the sense that it's unitary on some larger Hilbert space, but it's not unitary on the Hilbert space you're dealing with, because you're throwing away or ignoring the Hilbert space associated with the auxiliary system. Does that help? Is it still a little bit? So actually, what we'll do in a minute is, as I mentioned, I'm doing this backwards from my notes, where I'm giving the examples first, and then I'm going to build up the general theory. So hopefully, when we get to the more general theory, you'll see this will be more clear. If not, we can talk about it. Yeah.
This terminology, the oscillations that come from those equations, are those the Rabi oscillations?
Rabi oscillations refers to the NMR setting, and Rabi oscillations are the free oscillations under the omega naught. The Rabi oscillations is this piece.
Oh, I see.
It's undriven, yes. In general, we call the Ramsey oscillations are under driving. And it took me many years before I could remember which term was which. OK. So let's look at another example, which is NMR. And the beauty of this is that it's exactly the same mathematics. Totally different physical system. So in NMR, driving and relaxation. OK. So we're going to drive the two-level system with radio frequency electromagnetic radiation that will lead to coherent oscillations between the two levels, the two spin states, up and down. And we're going to also add phenomenological relaxation, which is this non-unitary process that drives the system to an equilibrium. So in NMR, we have the magnetic moment, the magnetic moment of the spin half nucleus couples to a static magnetic field called the Zeeman field. Along the positive z axis. And that gives us a natural Hamiltonian, which is time independent, of this form, where the coefficient omega naught includes a whole bunch of physical parameters. It includes the strength of the magnetic field. It includes the strength of the dipole. So for example, remember that for a nucleus, the dipole moment is in the opposite direction than for an electron, because the charge is different. So it includes a sign factor, as well as a magnitude of the dipole moment, of the magnetic moment. So basically, so omega naught, h bar omega naught over 2 is the energy splitting between up and down. And omega naught includes the field strength, B naught of the Zeeman field, and the magnetic moment, and the magnitude of the magnetic moment. Magnitude and sign of the magnetic moment. So what does this do? So this term, so H naught induces a precession about the z-axis. So of course, if you start out in an eigenstate up or down of sigma z, then there's no dynamics. If you start out in an eigenstate which is an eigenstate of sigma x or sigma y, which means you're in the xy plane, if your vector starts out, say, here, which has some component in the xy plane, then this induces a precession around the z-axis. You can think of this either as the quantum state vector, or remember the Bloch sphere, which we discussed. It's no coincidence that the Bloch sphere is the same name as the block of the optical Bloch equations, because here he was describing how does the state vector move around as a function of these kinds of physical influences. And the Bloch sphere is a great way to look at that. And you remember the neat thing about this, you can either think of this as the quantum state vector in this three-dimensional space, or you can equivalently think of it as the expectation value of the x, y, and z components of the spin. And those are equivalent ways to think about what this figure means. And so the point is that vector then will precess and lead to observables that change in time. Yeah.
So this is not a box sphere, this is a physical space.
Yes. But we can superimpose the labels for the Bloch sphere, in which this is z up and this is z down.
Because I was thinking, although we can think of the quantum state as a point on the surface of the Bloch sphere, we cannot think of that in space.
But you can, because this direction in the Bloch sphere is you can think of this vector as the vector of the expectation value of the spin components.
Right, expectation value.
Of the spin, or you can think of it as the actual vector psi in the two-dimensional Hilbert space. So, and this is because of the fact that SU2 and O3 are isomorphic, which doesn't work for a three-level system. So it's just a special property of. But so now that's not very interesting. If this is all you can do, then you're stuck in the 1950s. Now we can do much better things, which is we can induce a time-dependent field in the xy plane to drive transitions between up and down. So we can introduce a time-dependent radio frequency field in the xy plane to induce / control the system, well, to control the system and in particular to induce transitions between up and down. And it turns out that once you have a piece of your Hamiltonian that's proportional to sigma z, and a piece of your Hamiltonian that's proportional to sigma x and sigma y, then you have complete control over the system, and you can effect any allowed unitary transformation that you choose. So this gives universal control of the two-level system. But first, let me just write down the form of the interaction, and then we'll discuss what this means in practice. So again, we have omega is the RF frequency. And typically we have omega close to, but not exactly equal to, the Larmor precession. This is called the Larmor precession, this precession. And the idea is you want the frequency of the electromagnetic radiation to be close to omega naught so that you can drive that transition. And omega 1 is a factor that includes the strength of the electromagnetic field, the strength of the RF field, as well as parameters pertaining to the dipole moment and so on. And they all get rolled into a frequency. Omega 1 is the effective strength of the coupling. Between the RF field. The RF field is sometimes called the control field. And the magnetic moment. Okay, sorry, my handwriting is getting really sloppy. I'll try and be a little bit better so it's easier to read. And what else do we have? So, okay, so that's what omega 1 is. That's what omega is. And now what's happening here? We have this cos omega t, sine omega t. So what this corresponds to, so in this case, h1 of t corresponds to a rotating magnetic field. So the magnetic field is electromagnetic radiation of a frequency omega. And in addition to the intrinsic frequency of the radiation, which that basically tells you what the color is, although this isn't in the light spectrum, you have an additional frequency What? Sorry. The magnetic field, the magnetic field, the direction, I misspoke. The direction of the magnetic field is rotating at frequency omega. So this is actually the rotation frequency. This is the rotation frequency of the direction of the magnetic field. Now, it turns out that in terms of experimental capabilities, creating a magnetic field that is rotating in the xy plane is very hard to do. So this is a kind of a convenient mathematical picture that doesn't represent what people do physically in practice. So in about 5 minutes, I was going to get to the way we overcome this, which hopefully I'll be able to do. Okay, so so then as before, we introduce a notation delta, which is the same as before, which is the difference in the populations between up and down. And as before, we introduce the notation R, which is equal to the off-diagonal term. And then we get basically, we get the same equations. Which is here. Wow. And then in order to model relaxation, in NMR, we again introduce a gamma 1 process, which is a process associated with spontaneous decay of the levels of the energy eigenstates. And then in addition to that, we introduce a factor gamma 2, which is associated with dephasing. So in the NMR example, one has a gamma 2 here, which I'll write down in a minute, and gamma 2 is generally greater than gamma 1 over 2. So gamma 2 will include the dephasing due to the transitions between the energy levels from spontaneous decay, as well as additional physical noise mechanisms that lead to an attenuation of the coherence. So optics has this very clean setup where you can basically, an experimentally relevant limit is one where the only source of non-unitary processes is the spontaneous decay. But in the NMR setup, one is stuck with kind of two mechanisms in practice. And so one has essentially the same equations, the same as equations double star, which I'll label in a second, except with gamma 1 over 2 replaced with gamma 2, where gamma 2 is generally greater than gamma 1 over 2 because one has additional mechanisms of dephasing. So star star. And in the context of NMR, these aren't called the optical block equations, they're called the block equations. So I infer from this that, oh, sorry to you guys. I think Bloch must have done his work originally in the context of NMR, and then optics realized we can just use the same model for atomic decay. Oh, is it? Okay, so presumably this inference is correct with Purcell, yeah? Okay, so I don't have time to do so what we'll do next class then is, in practice, in terms of what's experimentally possible, or not possible, but experimentally feasible with present-day technology, is to create a magnetic field which is oscillating along x as opposed to rotating in the xy plane. And this leads to a slightly different picture, but it turns out it's approximately equivalent to this one in a certain limit, and that's called the rotating wave approximation. It's a very fundamental approximation that arises in many, many contexts. And so we'll go through that next class.
I just want to kind of read the gamma 1, the source of gamma 1. Is that just the thermal bath that the original atom was in, or?
Yeah. Yeah. So Well, gamma 1 is definitely due to thermal effects. It must be that there's also a spontaneous decay to the vacuum as well, just like in the atomic case, because, I mean, these are photons, essentially, very low energy photons. It might be that the magnitude of that spontaneous decay is so low that it's negligible, but I don't recall offhand the relative contributions. But right, those are two mechanisms that would lead to this. In practice, what the relative strengths of those are, I mean, I know that the thermal one is an important one, but whether the spontaneous emission one is important too, I don't recall.
And the sigma 2 are basically the similar kind of mechanism, but for
A gamma 2, you mean?
gamma 2, but for
Yeah, so I knew this at one point, the mechanism for gamma 2, but basically in NMR, the setup is, oh, maybe I should have mentioned this. The setup is you actually have some liquid, and that liquid consists of a whole bunch of molecules which are bouncing off of each other. And then we're just looking at the individual nuclei within each molecule. And so you have many, many copies. You have many, many copies of that one nucleus in each of the molecules in your solution. And your solution has Avogadro's number of copies. So in NMR, you actually read out that full physical ensemble. And so in a sense, the single-shot measurement of NMR corresponds to an ensemble measurement over an ensemble of systems. So you get the kind of expectation value, which is a virtual quantity quantum mechanically. But this is often forgotten because people are used to directly measuring expectation values. Well, you're only directly measuring expectation values when you're doing a measurement on a huge number of copies of the system. So anyway, so in NMR, you're doing this huge number of copies. Because it's a physical ensemble, they're actually interacting. Whereas a virtual ensemble, where you just do many repetitions of the same setup with an individual atom, of course, the atom doesn't have other atoms to bounce off of. It's just the one atom. So here you have many, many copies of these nuclei. And they're weakly coupled to the other nuclei in this solution. And so you have all these residual, excuse me. You have all these residual interactions between the nuclei of its neighbors with the nuclei in question. And that leads to essentially dephasing type noise mechanisms as well as transitions in the energy levels. And I mean, that's a whole complicated theory, which is well understood, how to kind of derive from first principles the expected magnitudes of these coefficients gamma 1 and gamma 2. OK, oh, yeah?
So is it true that the non-unitary decay means the decay is irreversible?
Yes. So yes with some caveats. So when I say non-unitary here, to be more precise in answering your question as well, it's non-unitary on C2. So it's presumably unitary on some bigger Hilbert space. But when we try and model this as a transformation on C2, two-level space, then it's not unitary. And then the question of irreversibility is subtle. So in the atomic setting, the gamma 1 process is irreversible when you only have access to the system. So if I have the ability to control the environment that led to this phenomenological decay, then I can reverse it. But in practice, we say it's irreversible because that's not realistic, having control over that complex environment. But remember I said that in NMR, there's a gamma 2, which is much greater than gamma 1 over 2. Oh, right. It's all coming back to me now. So one of the mechanisms that leads to gamma 2 being greater than gamma 1 over 2, which is the irreversible part of the noise, is the fact that, for example, because you have a physical solution with 10 to the 23 different molecules in the solution, your magnetic field, which gives you these Hamiltonians, omega 1 and omega naught, is not going to be perfectly homogeneous across the whole sample. So inhomogeneities means that the magnetic field will be a little bit stronger here and a little bit weaker there. So that means that this molecule is going to be, the nucleus in the molecule here is going to be precessing at one frequency omega naught, and the nucleus over here will be precessing at another frequency omega naught plus epsilon. And similarly, the RF control omega 1 will have inhomogeneities, so each molecule won't see exactly the same strength. So when you do your ensemble measurement, you're dephasing, you end up averaging over all these effects, which essentially if you have one vector here, and it's precessing around, and at time t it goes here, and your other initial vector precesses and goes to a little bit less far, then when you take the average of those two vectors, you get an attenuation of the average is attenuated. It's shorter than the initial two vectors because they're not aligned. And so the gamma 2, you'll get an effective dephasing of the coherence of the off-diagonal term due to that kind of an effect, that ensemble effect. And that is reversible. There are special techniques called spin echoes, which are designed to compensate for the inhomogeneities. And they allow you to push down the gamma 2 in NMR to as close to gamma 1/2 as you can using these techniques. So the question of irreversibility really depends on what kind of control are you allowing me. And so whenever we talk about irreversibility and the way that irreversible processes emerge from quantum mechanics, it's always about restricting what I'm able to do, and then things become irreversible under those restrictions. And then it's a subtle and important game to play to figure out exactly which restrictions apply under what conditions, so you can understand which things are reversible and which are irreversible. And that's extremely important to the question of control. Yeah?
So can we say that for each specific system, each specific nucleus, that there's not more decoherence than in the optical case?
Yes, I think that's a fair...
That it's just like because we treat all different systems as the same system, we introduce an error into our one particle system to account for the errors actually coming from effect. We use the same model for all different systems, as you were saying. Because,
yeah. So okay. So there are very good questions. There are very specific answers to all these questions. And I would encourage you to ask these questions to David Corey, who's probably the world expert on this topic. And I'm not 100% certain, because I know that in addition to these inhomogeneous effects, there are these residual interactions between the nuclei themselves. And I don't recall if those residual interactions account for only a gamma 1 and a gamma 1/2 here, or if they also lead to, in fact, my guess would be that you have a small, the gamma 2, due to those effects, is a little bit bigger than gamma 1/2. In NMR, they have gamma 2 and gamma 2 star, or T2 and T2 star, which is exactly addressing this issue of how much of this dephasing can you reverse using spin echo techniques, and which fractions can you not reverse using spin echo techniques. And so there's, I won't say any more about it because I don't remember the details. I knew this all at one time when I was working in David Corey's lab, but that was 10 years ago. And so some of this stuff has faded from my memory. But so let me just leave it at that.
David goes through some of the protocols for reversing spin echoes in detail.
All right, good. OK, well, thanks for your questions. Thanks for your attention, and I'll see you tomorrow.